How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for characteristics of gases and pressure. So let's take a look. Number one, which of the following statements about gases is false? Well, let's see. The distance between molecules of gas are very large when compared to the bond distances within the molecules. This is a true statement. All right, B, all gases are colorless and odorless at room temperature. That's not true. Not all gases have those properties. But let's look at the rest of them. Gas mixtures are homogeneous as long as they are unreactive. That is a true statement. Mix a bunch of gases together, as long as they don't react, they're going to make a homogeneous mixture. D, gases expand spontaneously to fill the container that they're placed in. Also a true statement. And gases are highly compressible. That is also a true statement. So which one of these is false? It's choice B. Whenever we have these kind of problems, I usually will do this little true or false just so I can keep track of what the question asks, because then you can go back and go, hey, they're asking for which one of these is false. Now I know which one is the answer. Number two, one important difference between gases and liquids is what? Gases are always mixtures. That's not true. You can have a pure gas. B, gases take up the volume of its container. That is true, and liquids do not, right? So that is definitely a difference. So B is looking good. C, a gas is made of molecules. Well, that's true for both of them, so it's not a difference. D, a gas can be both elements and compounds. That is a true statement, but that's also true for liquids, not a difference. And then E, all of the above are answers are correct. No. All right, so best answer, choice B. And number three, convert the following pressures into their new units. So here I got atmospheres that want kPa. So I know if I have 1.20 atmospheres, well, I know that one atmosphere is 101.3 kPa. So I do that math, atmospheres will cancel out, and I end up with 121.56 kilopascals. All right, B, 152 millimeters of mercury, 2 pascals. All right, well, if I have 152 millimeters mercury, I know that for every 760 millimeters of mercury, that gives me 101,300 pascals, roughly. But when I do that math and I multiply, my millimeters of mercury cancels out, and I end up with 20260 pascals. There you go. All right, 0.76 atmospheres to millimeters of mercury. All right, so I got 0.760 atmospheres. And I times that by, well, I know for every 1 atmosphere, there is 760 millimeters of mercury. My atmospheres cancels out. And when I do that math, well, let me find it. I get 577.6 millimeters of mercury. All right, and then if I have 1 torr, how many millimeters of mercury is that? That's just like 1, right? So 760 torr is the same as 760 millimeters of mercury. So you might not even need to do any kind of dimensional analysis for that one. All right, well, 1 atmosphere is how many torr? This is kind of another one of those that you might know right off the bat. That 1 atmosphere is 760 torr. All right. Number 4, the pressure exerted by a column of liquid is equal to the product of the height of the column times the gravitational constant times the density of the liquid, given here in that equation. P equals GHD. How high of a column of water with the density of 1 gram per milliliter will be supported by a pressure that supports 713 millimeters of mercury, given a density there? So we know that whatever pressure supports a column of mercury, well, let me do this. All right, so we know pressure equals gravity times height times the density of the material, right? So if it's the same pressure, gravity times the height of, let's say, mercury times the density of mercury has to equal gravity times the height of water times the density of water. So now gravity is a constant on both sides. That cancels out. And the problem's saying, hey, how high of a column of water? So it's asking for the height of water, and they give us the height of the mercury column, the density of mercury, and also the density of water. So I'd like to rearrange things first. I want to get the height of H2O by itself. So I got to divide each side by the density of water, and I end up with the height of H2O is going to equal to the height of the mercury column times the density of the mercury column divided by the density of H2O. So now I got it all rearranged. Now I can plug in my numbers. I have 713 millimeters for mercury times the density of 13.6 grams per milliliter divided by the density of water, which is 1.0 grams per milliliter. My grams per milliliter cancel out. I'm going to be left with millimeters, and the height that I get is 9700 when you do it to 2 sig figs. Yeah. All right, number 5. How many newtons of force are exerted on an area of 5.5 meters squared by a gas at a pressure of 325 torr? So first off, the newton. We know that a 1 Pascal equals 1 Newton per square meter. So first, we're going to want to get our pascals from our torr. So I have 325 torr times, well, I know for 760 torr, that's 101,325 pascals. So my torr will cancel out. Now I got pascals. Well, I can go, hey, I know that 1 Pascal is 1 Newton per square meter. My pascals cancel out. Now I got newtons per square meter, and then I times it by, hey, it's saying for 5.5 square meters. What do I get? And my meter squared cancel out. I'm going to be left with just newtons, and when I plug and chug and round it to 2 sig figs, I end up with 24,000 newtons. Yeah, that looks right. Cool. That's it. I hope you found that helpful. I think that's it. And I'll see you in class. Okay, bye.